So here in section 4.3, we're going to talk about the fundamental theorem of calculus. So you can see how that must be a very important topic to use the word fundamental. And it all has to do with this idea of differentiation and integration, which are inverse processes. And the integration is the one that we've been learning and talking about most recently. So suppose you have a continuous function on an interval. We're going to define a new function for area. So our new function is g of x, and g of x is the integration of the function f of t from a to x. Now what this is the area under f from a to x. I mean, it is a function of area. If you do this thing, you will get the area under the function f of t from a to x. That is what it will give you. You can think of it as area so far, because you're going from a, which will be a constant, to x, which is a variable. Something to understand, if x is a number, so let's say you go from 3 to 5, your interval is 1 to 100. If x is a number, then g of x is a number. And that's what we saw last section in section 4.2, was that idea of the definite integral. We started talking about the definite integral. Okay. So now our job is to show that f of x equals x on the interval 1 to 4. Okay, so here's how we're going to think about this. We're going to use the definition from above. We're going to define the function g of x, and that is going to be the integral, okay, from 1 to x of t dt. Okay, so we're going to integrate this idea here of just I'm using t on the inside because the integral goes from 1 to x. And I know you're saying, well, what about the 4? Well, the idea here is we're thinking about it in terms of like this x right here. So we're just thinking about what it would be to just integrate this from 1 to just some other value, like, something. Okay, so the idea here is we are finding basically this area right here. Okay, so understand that what we would need to do is find the area of this shape. So we're trying to, this part that I've shaded, that's what we're trying to find the area of. And what students typically notice is that here we have you might see it as, you see a triangle, you see a rectangle, and so we're just trying to add up kind of that idea of putting that all together. So I'll write that. So area of the shape, and that's just, again, from the definition from above, it's telling us that doing this will give us that area. Now it's going to be in terms of x, and I'm just focusing on my picture here. So, like I said, a couple different ways you could look at it. You could look at this triangle right here, and that triangle is going to be 1/2. Okay, so the area of a triangle is 1/2, and then your base, so the base here you can see is going to be x minus 1, and then the height of this rectangle. So understand that this height right here is just the same as the width, because this height here is just x, since this is x here, and we just have that line. So we have that, and then plus, and then the area here of this rectangle is simply going to be the x minus 1, because that's this distance here, whatever x is minus 1, because we're not including this, and then the height here is 1, so times 1. So you can see we have 1/2, we have x squared minus 2x plus 1 plus x minus 1. So that's going to be 1/2 x squared minus x plus 1/2 plus x minus 1. And then just combining that, we have 1/2 x squared, and then our x's simplify, and we have minus 1/2. Okay? And then, of course, the idea here is that g prime of x, so if we were to take the derivative of what we just found, and again, we found our answer here geometrically, you're going to just get 2 times 1/2, which is 1, minusing 1 from the exponent, you're going to get x, and then the derivative of minus 1/2 is 0, constant. So we get that g prime is just x. Okay? So the idea here was just to try to start seeing the relationship between this function g of x, which is the integral of a function over an interval. So the fundamental theorem of calculus part 1 says, suppose you have a continuous function and let g be defined by this area function, then the function g is differentiable. You can take the derivative of it, and the derivative of g is f of x. So that's the fundamental theorem of calculus here. And we'll look at an example right now. Well, first I gotta throw in a couple notes. Okay, so this says that all continuous functions have an antiderivative. So do remember that just because a function is continuous doesn't mean that it's differentiable at each point. But what we do have is that every function that is continuous does have an antiderivative, meaning you can take the antiderivative of it or you can integrate it. However, the fundamental theorem does not give a formula for it in terms of elementary functions. So it doesn't actually tell you how to take an antiderivative or the formula for antiderivatives. It just gives you kind of the big idea with the fundamental theorem. So a basic example would be to find the derivative of this function f of x. And understanding that what we have inside is this, f of t. So if we go back to the fundamental theorem, it says if you have f being continuous on some interval, and you have this g defined by, and then it's this integral, then you can differentiate g. But the big thing to understand is of the fundamental theorem is that g prime of x is just f of x. It is the function inside the integral using the variable x in this case, if your area function is g of x. So this is not actually wanting us to do any work at all. It's just wanting to see that because of the fundamental theorem of calculus, the derivative of f of x is simply your function but instead of t, the derivative here is actually using the variable x. And this is what the fundamental theorem says is true. And you can see that it's using that idea of, derivatives and antiderivatives being opposite processes, so that if we have something that is an integral, but we take its derivative, we can simply replace the variable in the integral with our variable there. And when you think about that 3, it really is arbitrary. It doesn't matter. And there is an aspect of taking derivatives and constants going to 0 and things like that. So that's part of that as well. But that's all we have to say for that answer. And we just want to remember that our function here, f of t, is continuous, on certain intervals. Obviously, there might be issues here or there, but there are intervals for which you would be able to do this. Okay, so let's just take a look at some more examples of this. So if you want, you can pause and see if you can get the answers, or you can wait And or you can just watch it, whatever you want to do. But here, I want you to notice it's just a little bit different because the x is in the denominator, so we're just going to use the things that we've learned from previous section 4.2, I believe, where we are just switching our signs. So we're, instead of going from x to 1, we go from 1 to x, and that makes us have a negative. So that's all that that is. However, the idea behind me doing this is just because I can't use the fundamental theorem until I have it of the form that you see in the fundamental theorem of calculus. So without writing it as a constant to that variable, I wouldn't be able to actually use the fundamental theorem. So now I can use it. So I have g prime of x, and we know that that is going to be, so I'm still going to have that negative because that's a constant on the outside, but basically taking this piece here, we know from the fundamental theorem that this is just going to be sine of x over x. And that's it. That's all it wants you to do. Over here, notice this problem is slightly different. For C, it has a constant on the denominator and it has a variable in the numerator, but it's not just x, it's x squared. And so in order to use the fundamental theorem, we're going to have to replace that x squared. And this is where, you know, we typically would see some sort of substitution. So we say let u equal x squared. And so understand that u is a function of x. So g of u is now 0 to u tan of t dt. But again, the idea here is this allows me to now use the fundamental theorem, which I couldn't in the way that it was written with C. So in doing this, now I can take my derivative. So I will have understand that if we want g prime of x, we're going to have to do g prime of u times u prime of x. So it's essentially becomes a chain rule problem now. And so that's simply going to be, so g prime of u is now using the idea of having tan u, okay, because that's, I'm using the fundamental theorem here for the fact that I have a u up here. So I have tan of u, great, but then I need times and then u prime of x. So I just need the derivative of u, which is going to be 2x. And so that's going to give us tan x squared times 2x, or if you want, 2x times tan of x squared. So notice that your thought might be, oh, isn't it just tan of x squared? But it's not, because you don't have just x at the top, and the fundamental theorem requires just a variable, not a variable squared, not any kind of variability, I should say, in the variable. But that's just the answer of that. So the g prime of x is actually tan of x squared times 2x. Okay, so the proof of this, the reason that the fundamental theorem is true, seems important. Okay, so the proof of the fundamental theorem is basically proving that g prime of x equals f of x. G prime of x equals f of x. So we're going to take ourselves back. The derivative of g prime is just the limit as h approaches 0 of g of x plus 8 minus g of x over h. So that's just, there you go. Now I'm going to rewrite this using the definition of g of x, which is given in the first part of the fundamental theorem. So I'm going to replace, so limit as h goes to 0, and let me give myself a little more space here on the bottom. I'm going to have the integral, because again, this is what g of x is equal to, of a times x plus h, and then inside you have your f of t dt minus, and then we have a 2x of f of t dt. So again, this is by definition just from the beginning of the fundamental theorem. And then that's going to be over h. So we're trying to show that this thing is just equal to f of x. That's all we're trying to say. Okay. And I'll mention for the video that I am the random piece of information that I'm recording this video on a Monday morning. Okay. So then this is the limit as h goes to 0 of x to x plus h of f of t dt over h. But then the big question is, I mean, what is this thing? You're trying to show that this is f of x, and it's like, there's a lot there. So we're trying to show what that is, so we're going to use the idea of bounding. So let little m of h be the absolute min, and this big M of h be the absolute max of, well, I can just say the max on the interval x to x plus h. Okay, so these are just numbers. So it's whatever is their absolute maximum and the absolute minimum. And the extreme value theorem is what tells us that those things exist. So what we're saying here is that this function is less than or equal to m, big M, and greater than or equal to little m. So now if we integrate x to x plus h of f of t dt, you want to think about the fact that if we do that to all three sides, if you integrate just a constant, you want to remember that the integral of just a constant on an interval is the constant times the length of the interval, because it's just a rectangle. So in this case, the length of the interval, because you're going from x to x plus h, the length of that is just h. So you have this, m times h less than big M times h. Okay, so now if we think about the fact that we still need to take the limit as h goes to 0 and we still need to divide by h, we can now divide by h, and that's just going to give us m, and then we're going to have x plus h, f of t dt, and this is all over h, and then down here, over here I should say, less than or equal to m. Okay, we're almost there. So then we're just going to bring it up here, and now we still have to take that limit. So we're looking at the limit as h goes to 0 of m less than or equal to the limit as h goes to 0 of x to x plus h of f of t dt over h less than or equal to limit as h goes to 0 of m. So now the idea here is to understand that although little m and big M are constants, if you're looking at the limit as h goes to 0, and if little m and big M are within this interval x to x plus h, then as h goes to 0, these values basically just approach the function, whatever that function is on that interval x to x plus h. And so what that creates and what that gives us is actually that the limit as h goes to 0 is f of x. And on the other side, we also get f of x. Because again, as h goes to 0 on that interval, that absolute maximum and absolute minimum are approaching whatever the function is, which is f of x. And then in the middle here, we have the limit as h goes to 0. So I'm just rewriting it here, x to x plus h, sorry for the small spacing, f of t dt over h. But for many of you, you probably understand that now I can say, I won't put it there, so by the squeeze theorem, so bringing back the squeeze theorem, by the squeeze theorem, and again, come back to the original here, g prime of x, because that's what we were showing what that was equal to, equals f of x. Okay? So it exists and is equal to f of x.